So first, let me introduce our speaker today. Alex Condello is the Director of Algorithms, Performance, and Tools at D-Wave. His responsibilities include the Ocean Quantum Software Development Kit, D-Wave's suite of quantum tools, benchmarking, the development of hybrid algorithms that combine classical and quantum resources, such as what you'll hear about today, and professional services. Alex earned a Master's of Applied Science in Mathematics from Queen's University in Canada. So welcome, everyone, and welcome, Alex.
Awesome. Thanks, Susan. Hey, everyone. So as Susan said, my name is Alex, and I'm really excited to be here today to talk to you about assessing apps for hybrid, or to put it probably in the framing that you might have in your mind right now, can hybrid help you solve your business problem? I think a lot of you are here probably to try to figure out, is quantum computing and hybrid computing useful to you? Can it provide value to me? So I'm hoping today to talk a little bit about what sorts of problems are good for hybrid solvers, what sorts of problems can be solved by hybrid solvers, and to help give you a little bit of guidance on maybe how to get started on doing that assessment or even taking your first steps towards solving those problems. So I want to start off by defining a hybrid solver, because we are going to be talking about them throughout this whole talk. A hybrid solver is nothing more than a solver that uses both quantum and classical resources to solve problems. So if it's using both a quantum computer and classical resources, it's a hybrid solver. At D-Wave, we actually provide 3 different hybrid solvers via our LEAP platform. The first is our constrained quadratic model solver. The second is our binary quadratic model solver. And the third is our discrete quadratic model solver. If there are some sort of differences between these, which I've outlined on the slide, we're actually going to be focusing today, though, almost entirely on our constrained quadratic model solver. And I'll be describing over the course of this talk what it means to use integer variables or binary variables, what it means to have constraints and all those sorts of things. So the distinctions between these solvers don't matter too much. It just suffices to know that we do have several of them available in LEAP right now. You can sign up for LEAP for free if you haven't already and get some free time on those solvers and to get started with your application. So a question you might be asking yourself is, why is this talk focused on hybrid? Why are we talking about the hybrid solvers rather than, say, the quantum computer directly, or even compared to, say, classical solvers? So from my perspective, at least, there are 3 main benefits to using hybrid solvers. The first one, and in some sense, this is actually the most important, is a benefit of abstraction. The problem that is consumed by the quantum computer is fairly understandable. In fact, I would encourage anyone who's interested to go check out our examples and look at how to do this, but it is fairly specific. It's a little bit low level, it's unconstrained, it has some sort of pickiness about it. Whereas the hybrid solvers allow you to specify your problem in a language that's hopefully pretty native to your business problem. It can be specified in a way that sort of is clear and makes sense without having to do a lot of transformation or changing of the type of problem in order to map it to the quantum computer. The hybrid solver takes care of all of that for you. It dispatches to the classical resources, it dispatches to the quantum resources. You don't have to worry about any of that. The second main advantage to our hybrid solvers is scale. So our current Advantage processor solves problems with about 5,000 variables at the largest scale, whereas our hybrid solvers can solve problems with up to 500,000 variables. And most of the business problems that we run into when we're working with customers or we're working with researchers are actually in this sort of like tens of thousands to hundreds of thousands of scales of variables. So quite a bit larger than what can be solved sort of directly on the quantum computer. And so again, a hybrid solver is more flexible in this way. You can sort of take your large problem and just submit it directly and let the hybrid solver sort of do all of the work of figuring out how to handle that scale. And finally, the main reason, and this is in some sense these are all important, but another important reason of using the hybrid solver is performance. By using both resources, we can achieve state-of-the-art performance. And of course, performance is ultimately what's important to you all. You want to, get the best possible performance you can on your solver. If we couldn't give you good performance, you wouldn't, come to us in the first place. Okay. So having defined what a hybrid solver is and justifying why we want to use it, I want to focus in on the life cycle of a problem. So, when you work with us, or really when you try to solve any problem, there are a few different steps that you're going to go through. The first step is probably the level that you might be at now, which is the business problem. You have a problem in your mind. You have a problem that you want to solve. I want to allocate I want to schedule my employees. I want to route my trucks. I want to fold my proteins. I want to detect fraudulent activity on my platform. I want to make a bunch of money on the stock market. These are business problems. This is sort of a high-level problem that describes in, hopefully a little bit specific, but possibly quite general terms, what it is that you want to accomplish. Having then sort of started with your business problem, the very first step that we would take with you as part of one of our programs, or the first step that you would take if you were doing this by yourself, would be to create a technical specification. Turn that business problem, which is fairly general, into a set of technical statements. What is the number of trucks you would like to route? How much risk are you willing to take on in your financial investments? These are the sort of numbers that underpin the business problem that you want to solve. How much time do you have to run? What's the quality of solution that you would want to see in order for us to be able to provide value? Okay, so you now have a technical specification, a sort of description of all of the things that you want to do. The next step is your mathematical formulation. That's turning this into the mathematical problem that describes the math equations that describe your business problem. From there, you turn it into a model. Those are the bytes and biases, putting it onto a computer, consuming it so that a solver can consume it, and then finally submitting to the hybrid solver. I spent a lot of time on those first three steps and not so much on the last two, and that's deliberate because this talk is going to be predominantly focused on those first three steps. Because once you've gotten to the mathematical formulation, you're, from a business perspective, you're pretty much there. Getting it into a model and then submitting it to the solver, those are relatively straightforward. We have tools to do all of that. There's other talks that describe how to do that. So for right now, and for this talk, I'm going to be focusing on those first three steps. So I think that often these things go more smoothly when you have an image in your mind of the problem that we're solving. So I'm actually going to quickly switch to a demo just to give you sort of a problem that you can be familiar with and sort of get in your mind as a sort of business problem that you might have. So let me change screens. So I'm going to be starting here on our open source feature selection CQM demo. I then clicked this button, this Open in Leap IDE. This opened up our online integrated developer environment, which then opened up the demo. So like all of the demos that we do at D-Wave, this is running live. This is running in our online integrated development environment in Leap. If you signed up for Leap and you had an account, you could click for click follow everything that I'm doing in this demo. So in this case, the business problem that I want to solve is I have a bunch of information about different passengers on the Titanic, and I would like to predict whether those passengers survived or not. That is the business problem that I want to solve. The data that I have for each passenger looks like this. I have, what ticket class they had. I had their reported sex, their age, what fare they paid, what cabin they were in, whether they used, which honorific they used, Miss, Mr., etc., whether they were traveling alone, and what port they got on in. These different characteristics also have some redundancy amongst them. And so, for instance, whether you used the honorific Mr. is quite correlated with your reported sex. Which port that you got on is quite correlated with the others. You probably, if you got on at port C, you didn't get on at port S. So when you have this this is the sort of step, and the business problem that I have is I would like to pick a smaller number of these features to use to make my decision. I don't want to have to look at all of this because there's redundancy. I want to pick a smaller subset in order to have fewer things to track and hopefully actually to improve my predictions. So for instance, if I wanted to pick exactly 4 features, I can actually submit this problem to the hybrid solver and use the hybrid solver to pick the 4 features I want to use to make my decisions for me. As always, this is running live in Leap. So that actually just got submitted to our hybrid solver, which actually submitted a problem to the quantum computer, and it's come back with a solution. And it's actually picked the solution that makes sense. We see that we have 4 pretty good quality solutions, and there's not a lot of redundancy between them. So it has, in fact, accomplished the goal that we would expect. Now, I want to mention that there's a lot more to this demo. I would really encourage y'all to check it out. We also actually gave a webinar about a month ago that goes through this in a lot more detail, describes a lot better the method that we were using, and shows, there's another data set that you can see. There's all sorts of other information, and I would really encourage you to check that out after you're done watching this one. I'll provide a link at the end of the presentation to that demo. Okay, so I'm going to switch back to the presentation. Okay, so as I said, I wanted to give you sort of a visual representation of these feature selection style problems. And now let's back to our regularly scheduled programming. Okay, so let's take another feature selection problem. In this case, the business problem would sound something like this. As the chief of information security at Business Incorporated, I need to know what user actions are associated with malicious behavior so that I can identify hostile attacks before they happen. So that's the business problem. This is sort of what someone would, maybe come up to me at a conference and talk about, or if you were going through our launch program, which is our program for helping you to solve your business problems using hybrid solvers, this is where you might start. From there, you might create a technical specification. That technical specification in this case might sound something like, there are n different actions that a user can take in my system. They can enter their password, they can, they can change their birth date, they can, open up a resource, they can see, they can pay their bills. These are different actions that they can take within the platform. I would like to choose k different actions to monitor and flag. This is where that feature selection comes in. There are a subset of those actions that I would like to use to make predictions. Many of those actions are correlated. So just like in the Titanic demo, the actions might be correlated. The action of entering my password very often comes after the action of entering my username. Those two things are very correlated. I might not need to monitor both of them. Monitoring one of them might suffice. And finally, I have a database of those past actions, of those users, their actions, and whether they were benign or malicious. So I have something to work with. From there, we can turn this into a mathematical formulation. The mathematical formulation looks like this. And if you're not sort of super big on the math formulation, that's cool. If you are, that's also cool. The math formulation ends up looking like this. We have a set of binary variables. These are these x's. Those represent the decisions. And we want to minimize this function relative to a constraint that would pick exactly k actions. Again, I'm not going to go into the math in sort of excruciating detail. Just know that this is what the actual math equation that governs this business problem looks like. And then finally, you want to turn that math equation into a model and submit to the hybrid solver. We have an open source example that goes through that in great detail if you want to check it out. Okay, so I've sort of described for a specific business problem what going through these first three steps looks like. But now I want to walk backwards through those steps, starting from the hybrid solver, to explain why this was a good app for hybrid. So if you want to do that, you need to know what the problem is that is solved by the hybrid solver. Our hybrid solver, the one that I'm focusing on today, is our constrained quadratic model solver. And the constrained quadratic models have three aspects associated with them. The first is that they have variables. These are the decisions that you want to make in your problem, your business problem. This is, I want to monitor this behavior, yes or no. That is a binary decision. I want to load 27 boxes into this truck, or how many boxes should I load into this truck, really, is the integer variable. It's going to tell you how many, the value assigned to that variable will tell you how many boxes to load. This is the amount of risk that your portfolio can take. That is what the continuous variable would tell you. It's a sort of, any number, or this is how many dollars it will cost to ship your items across your supply chain. These are the continuous variables. The second thing that constrained quadratic models have are constraints. These are the rules that govern your business problem. These are, for instance, on the feature selection case, this is, I want to pick exactly k features to monitor. But this might also be something like, my truck drivers need bathroom breaks, or there are rules on how much risk I can have in my portfolio, Or, these are the physical laws that govern my protein folding problem. These are all constraints. If a solution doesn't meet those constraints, it's not a feasible or valid solution. And finally, constrained quadratic models have quadratic interactions, which is just to say that those variables have interactions amongst themselves. In the feature selection example, it was that there is those correlation amongst them. This quadratic interactions thing is definitely the sort of hardest to get your head around. So I will just say that it is there. It's a feature of good problems, but it's also in some sense not the most important to have in mind. If you have those first two, you're already in great shape. Okay, so now mapping those criteria directly onto the feature selection problem. As I said, there are n different actions a user can take. So I have a set of binary variables that will tell me whether I should monitor each action, yes or no. I would like to choose k different actions to monitor. That is a constraint, which is that I want to choose exactly k of them to k of those variables. Many of those actions are correlated. This is that quadratic interaction I was describing. Those variables have interactions amongst themselves. And finally, there's a database of past users, their actions, and whether they were benign or malicious. Now, I haven't mentioned this as one of our criteria, but this is important. There is data to work with. There isn't a problem to be solved. This is so important that I made it its own slide, which is just to say, in order to make use of a hybrid solver, and in order to formulate a problem, you must have data to formulate that problem from. It is definitely the case that sometimes your business problem is lack of data. I've had people come up to me at conferences and say, hey, I have no idea what's going on in my factory. Can you help me with that? And the short answer to that question is, that's a little tough. If you don't even know what's going on, I can't help you make your factory better. You have to know what's going on in the first place. Now, in principle, you could maybe use a hybrid solver to help come up with a good strategy for, what sort of sensors you want to put on your assembly line. But in general, if you don't have a problem, if you don't have the data for us to be optimizing over, it's really tough for us to come to good solutions. So that is one of those sort of hidden requirements. Okay, so I've gone sort of in and out on the feature selection problem, and I've shown you a demo, and I've hopefully sort of explained a little bit why that was a good application for hybrid. So now I want to go forwards again one more time, this time on a different problem class to sort of apply the lessons that we learned from the last one to the problem. So in this case, the example I want to run with is 3D bin packing. And in this case, the business problem would sound something like, as the manager of shipping at Delivery Limited, I want to pack a fixed number of differently sized boxes using as few shipping containers as possible so that I can minimize the shipping costs. So again, if you're the kind of person, if you've been paying attention to the way that we've the criteria that we have, you might actually already be hearing in that business description the technical specification that ultimately, what we want, the constrained quadratic model, the mathematical formulation for that. But just to make that explicit, we can take the technical specification from that business vision, which is that I have k shipping containers available, and we know right away that those are binary variables. Each shipping container can be represented by a binary variable. The next part of the technical specification is I have n boxes to place. Whether I place one box into a different container, that's another binary variable. There's another decision to be made there. Each shipping container is 40 feet by 8 feet by 8 feet. This is a constraint. This is a rule. I can't have my boxes outside of the shipping container. They can't be halfway through the wall. And finally, there's an interaction there between the variables, which is that the variables that represent which box each container each variable is in, and where the box is, those have an interaction amongst themselves. And that's those quadratic interactions that we were describing. So again, from that business problem, you can sort of start seeing the shape of the CQM underneath. So I'll mention once more that this actually has an open source example that goes through all of this in great detail. If you're interested in checking that out, I would encourage you to go to our GitHub account and see our 3D bin packing example. We also have a webinar about that. In fact, we actually have a lot of great resources to go to. You can see all sorts of these different demos. You can see lots of different versions of how we solve these problems by following any of these links here. And finally, I'll call out our launch program, which is our program for helping you solve problems, where we can come in, we can look at your business problems, we can help you do these steps that I've described, and then ultimately, hopefully to return, value to you, the customer. And with that, I will take questions.
Okay, thanks, Alex. So we've had a number of questions come in, some of which have been answered. I'd like to remind our panelists to please mark some of the questions that you think would be most beneficial to the audience for Alex to answer. But here's one I thought would be of interest. I had thought of hybrid as being a strategy rather than just a tactical response to addressing the current limitations of quantum capacity. Do you believe that some current hybrid use cases will migrate to pure quantum solvers as the technology progresses? If you do,
please.
If you do, how quickly do you see this transition, and how do you see the development of algorithms to prepare for such changes? We need to minimize downtime.
Okay, yes, I have. It seems like I have misled you. I definitely agree with that it is a strategy, not a stopgap. So I believe very strongly that forever, that hybrid will be the main use of computation forever, because we're already doing this even in the purely classical space where we're using CPUs and GPUs together. Nobody's solving problems only on GPU. And just that way, in the far future, even as our quantum systems get larger and get more powerful, I still expect that there will be many things that the classical systems can do better and some things that the quantum system can do better. And so you're going to want the best of both worlds together.
Okay. Next question, since we are looking at feature selection, if a problem has 1,000 inputs, in most cases, I would imagine that the user does not know the magic number to keep. I think it would be good for the feature selection method to be able to select the number of inputs that are the most important. I have not seen this feature in any demo. Does it exist?
So sort of two-level answer. So we do have a feature selection plugin to scikit-learn, which I would encourage you to check out. Scikit-learn itself provides a lot of great tuning strategies. So you can actually use our feature selection plugin out of the box with the scikit-learn's tuning to find the optimal number of features. You can have scikit-learn sort of pick your number of features based on a lot of different criteria and sort of tune that parameter. Now, there is sort of a second level to the question you're asking, which is like, could we use the hybrid solver to pick the optimal number of features? I don't offhand know of a way to do that, but I think it's a great question, and it does fit the criteria that I'm describing, which is that there's an optimization problem here and there's a set of constraints. So that definitely can be represented as a hybrid problem, and maybe that's a really interesting approach to take.
Okay. Does the maximum 100,000 variables mean binary variables?
So our CQM solver can take up to 500,000 variables, and they can be any combination of binary, integer, and continuous.
Okay. Do hybrid solvers solve NP-hard problems?
Yes. I mean, it is worth mentioning. They solve, yes, they do. It's worth mentioning that these are heuristic solvers. The quantum computer is itself probabilistic. So it's not that they can't provide a certificate of optimality, but they do take as their bread and butter NP-hard problems. I mean, you can submit polynomial time problems to them. It's just a little bit using a bazooka for a nail. So yeah, we predominantly are interested in solving NP-hard problems.
Okay. Many optimization problems can be solved classically, e.g. via simulated annealing. Are there any rules of thumb or guidelines that may suggest the quantum solver is better for that problem than the classical solver? Anything that would reduce the amount of experimentation or testing?
So what I would, at this point, I would point you to some of our literature. We have a couple papers, including a recent one in, I think it was in Science, or was it Nature? Susan, help me out.
It was Nature.
Nature, thank you. Describing sort of in great detail, like what the quantum computers are best at solving, what sorts of problems. We also have a result from, maybe 6 or 9 months ago, sort of describing the same thing. I would say that the rules of thumb for the quantum computer itself are quite, or the quantum computer by itself are quite complex, even as rules of thumb. If you're solving problems directly on the quantum computer, I would say that, unconstrained binary problems are where you want to start. But the advantage of hybrid solvers is that they actually extract those sorts of problems from your constrained integer and continuous problem and submit them to the quantum computer. So they find these sorts of problems in the overall problem and use the quantum computer to solve those problems. So you don't have to think about that. In terms of having intuition for the hybrid solver versus some of its classical competitors, I mean, there are other classical solvers that solve the same problem class as our hybrid solver. I would say that we're really interested in the discrete problems, so the ones that are heavy on binary and integer variables and light on continuous variables, and we're really interested in the quadratic problems, so the ones that have quadratic interactions amongst those variables. We do solve linear continuous problems, we do solve linear problems, we solve all sorts of varieties here, but the ones that we like the best are the ones that are on that sort of closer to it, that have a lot of binary variables and a lot of quadratic interactions.
Okay. Do you see any opportunities for hybrid solvers to be integrated into applications relying on output from large language models?
Yes, definitely. I don't know of any examples offhand, but I definitely think this is something we'll see in the next few years.
Okay. Let me just run through and see if there are any more. We do have our panelists answering some questions here. How much data is minimally sufficient for a general use case? Is there a simple formula?
Short answer, no. I will say that the quality of the solution you get out is going to be based on the quality of the data you put in. So if you have a lot of uncertainty about what's happening on your assembly line, then we can optimize given what we know, but the quality of the solution out will be sort of proportional to the uncertainty that you have. When it comes to things like feature selection, the feature selection is an interesting example because it's actually often best used in cases where you have a relatively small amount of data relative to the number of features that you might be able to select over. So you have sort of more features than you have data points. You have more information about the passengers on the Titanic than you have passengers on the Titanic. And that's actually where feature selection often is useful. So, long story short, on a gut level, your uncertainty about the thing you're optimizing is going to be correlated to the quality of the solution you get.
Okay. Do you have any idea how long a problem using BQM of 1 million variables takes? I guess
I don't know offhand the minimum time limit. I will say that our hybrid solvers have a sort of minimum runtime that scales with the size of the problems. That's why I don't know offhand what the minimum time limit is for a million variables BQM. But the runtime is sort of is a function of how difficult your problem is. So very often the way this happens in practice is that a company will say, or a customer will say, I have 10 minutes to run this problem and I want the best possible solution I can get within 10 minutes. And the question that's being asked is the solution provided by the hybrid solver good enough and better than the other thing they could do in 10 minutes? Or conversely, I have a certain quality of solution and I want to know what's the minimum amount of time to get there. So I have a certain amount of trucks that I need or I want to minimize the total number of miles. I can't drive more than this number of miles. And so how long will it take me to find a solution that meets that criteria? And in that case, it's really a function of sort of how difficult the problem is.
Okay. The hybrid CQM is very straightforward to use, but lacks control in the sense that the only option is time limit. In your opinion, would you get better solutions in something purely quantum and having the ability to configure the wealth of options available to them? Also, is there a way to get additional timing information from hybrid CQM besides QPU and real-time measures like you can from the purely quantum solvers?
So I would say that unless you have a fairly specific problem and fairly deep knowledge, in general, you'll get better performance even with the fewer options that the CQM solver has. And then in terms of getting more time or more information about the timing or more parameters of the CQM solver, I would really encourage you to open a feature request in our community. I will say that this is something that we've thought about. It's an area of internal discussion, weighing that against the ease of use arguments. And I will say that people's feature requests in our community get a lot of weight. So having that written down and sort of saying that this is something that you want would help inform that discussion.
Okay. Is runtime a function of problem complexity or the number of variables? Is it exponential? Is it some other function? What are the general rules here?
Yeah, so okay, so there's a couple things that are happening here. So the first is there is a minimum runtime, which is a function of the number of variables. This is essentially the minimum amount of time to do something on the problem, to do a couple submissions to the system, to the quantum computer, to run a bit of some of the classical algorithms that are underpinning it. That's the minimum runtime. That's distinct from the time to solution, the expected amount of time it would take to get to a certain quality. So in general, the longer you run the solver, the better solutions that you'll get, although you'll eventually run into diminishing returns. It's worth stating that for these NP-hard problems, the expected runtime, so the amount of the expected runtime to a certain quality of solution is expected to grow exponentially. That's sort of the worst case. In practice, we often don't find that to be the case. For many, many business problems, you can get away with much smaller runtimes. So these runtimes will be anywhere from seconds to minutes. I think the longest problem that I know of that's sort of in danger of getting into production is on the order of tens of minutes. So, but some folks have run the solver for hours as well. So there are, it really depends on the sort of difficulty of the problem.
Okay. Well, let's got one more question before we go. The nirvana state would be automated orchestration of runtime in real time from the single code set to allocate compute activity to the solver best place for an accurate and rapid response. Anybody looking at this?
I would say that is nirvana. I'd say there are lots of people looking at it. I don't know of how to do it at the moment, and I think the community would be very interested if we could figure it out. So yeah, it's an area of active research, and there are sort of various things you can do to get close. Something that for instance comes up occasionally is being able to specify a target quality of solution and use that as your exit criteria rather than time. But yeah, it's in general, sort of appropriately allocating these resources is a very difficult problem. I think the hybrid solver has gone very far in that direction. It's the most sophisticated solver for allocating resources to quantum and classical resources, certainly that I know of. But also there's still a ways to go. Okay,
well, we have a few more that keep coming in. We have time for. So is there documentation on how a model is turned into the quadratic problem solved by QPU? I mean, how is it mapped to the sparse matrix that the QPU can handle?
Unfortunately, right now, the specific way that the hybrid solver makes use of the QPU is proprietary.
Okay. For the distribution of solution quality sampled from the solver, do we have any generic metrics to evaluate the rate of contraction toward the minimum over increased annealing time?
Annealing time, I would have to ask the person asking the question if they're referring to the annealing time. Implies to me they're thinking about the quantum computer, or are they referring to the hybrid solver? I guess I can give both answers. Okay. So for the hybrid solver, one thing that you can do is you can run for sort of increasing amounts of time, and you can sort of plot a burn down and use that to figure out when it's converging. And then for the quantum computer, more or less the same answer. That's sort of the best way to get at it.
Okay, well, our panelists are answering a few more, but I think we've come to the end of our time today. So Alex, thank you very much. Again, for everyone online, this has been recorded. It will be on the D-Wave YouTube site tomorrow. We can also make the slides available. And we encourage you to get a Leap account if you don't have one, and to run some of these demos yourself. And again, go back and take a look at some of the previous webinars we've done. There's a lot more information about a lot of the areas that Alex talked about today. So thank you all very much for coming. Our next webinar will be at the end of May, presentation on sensor optimization, and you'll get an email from us with information about that. So thank you all very much. Alex, thank you. And thank you to our panelists.